Hello friends, this is Gopal Sharma. Welcome you all in csirnet lecture series. This is lecture 3rd of linear algebra. In the last lecture, we have done some important results in vector space. Okay, if you have not watched that video, please watch it. The link is in the description box. In this lecture, we are going to do some important problems which were asked in csirnet exams. So without wasting time, let's do it. The first problem is, let W equal to set of P of B such that P is a polynomial with real coefficient where B is the 3 cross 3 matrix. Okay, then the dimension D of the vector space W satisfies. The first option is D greater than equal to 4 less than equal to 6. Second option is D greater than equal to 6 less than equal to 9. The third option is D greater than equal to 3 less than equal to 8. And the fourth option is D greater than equal to 3 less than equal to 4. So how can we do this? W is given. Set up all those P of B such that P is a polynomial with real coefficient and V is a matrix. Let's say P of X is a polynomial a0 plus a1x plus a2 x square plus and so on an x to the power n, where all those ai are real. Okay. Now P of B will be equal to a0 into identity matrix plus a1 into B plus a2 into B square plus and so on an B to the power n. Okay. See, this P of B is a linear combination of identity matrix B square and so on B to the power n. That means every element of the vector space W is a linear combination of identity matrix B square and so on B to the power n. That means W is a span of I, B square and so on. Now use the result that if vector space B is a span of I, C square and so on, where C is a some n cross n matrix. Okay. Then the dimension of this vector space B is nothing but the degree of minimal polynomial, degree of the minimal polynomial of matrix C. This is the very important result. Okay. See, here our vector space W is a span of identity matrix B square and so on. So the dimension of this W will be equal to the degree of the minimal polynomial of B. Okay, because minimal polynomial is the smallest degree polynomial such that B is a root of it. So let's find out the minimal polynomial for the matrix B. Let lambda is an eigenvalue of matrix B. Then determinant of B minus lambda I equal to 0. This will implies that the determinant of minus lambda 1 0 0 minus lambda 1 1 0 minus lambda will be equal to 0. Now its determinant is equal to minus lambda times lambda square minus 1 0 minus 1 equal to 0. This implies lambda minus of lambda cube plus 1 equal to 0. This implies lambda cube minus 1 equal to 0. This is the characteristic polynomial of matrix B. This implies that lambda cube equal to 1. Okay, the matrix B will satisfy its characteristic polynomial. That means P cube will be equal to identity matrix. From this we can conclude that B square are non-zero matrix. Okay, and B cube, since B cube is identity matrix, therefore W is equal to span of identity matrix B and B square, and B cube is identity. So this you can check it. This set is linearly independent set. Okay. So since the dimension of vector space W is equal to 3, this implies first option is wrong, second option is also wrong, third option is right, because D is greater than equal to 3, less than equal to 8, and D option is also right. So C and D are correct option. Okay. Now the next problem is, let C be a n cross n real matrix. Let W be the vector space spanned by the set I, C, C square and so on, C to the power 2n. Then the dimension of the vector space W is. This is the similar problem which were asked in June 2012 in part C. Okay, this is the answer is in one line. Okay, W is span of this set, so the dimension of W is equal to degree of minimal polynomial of C, minimal polynomial of matrix C. C is a n cross n matrix, so the characteristic polynomial of this matrix C has degree less than equal to n. So the minimal polynomial of the matrix C has degree less than equal to n. Okay, so the dimension of W will be less than equal to n. That means the dimension of the vector space W will be at most n. So the B option is correct. Now the next problem is, this was the problem which were asked in csir exam December 2012 in part C. Okay, the problem is, let n be an integer greater than and equal to 2, and let M and R denote the vector space of n cross n real matrices. Let B belongs to M and R be an orthogonal matrix, and let B transpose denote the transpose of B. Consider WV equal to B transpose AB such that A belongs to M and R. Then which of the following are necessarily true? WB is a subspace of M and R, and dimension of WB is less than equal to rank B. WB is a subspace of M and R, and dimension of WB equal to rank B into rank B transpose. WB equal to M and R. WB is not a subspace of M and R. So first we need to check whether WB is a subspace or not. So use the subspace test. Okay. Let B transpose A1 into B and B transpose A2 into B are two matrices in the space WB. Okay. Then WB will be a subspace of M and R if alpha times B transpose A1B plus beta times B transpose A2 into B belongs to WB for every scalar alpha and beta in the field R. Okay. See, this thing is equal to B transpose alpha times A1 into B plus B transpose beta times A2 into B. Further, this is equal to B transpose alpha times A1 plus beta times A2 into B. So since A1 and A2 are matrices in M and R, so alpha A1 plus beta A2 is also a matrix in M and R. Okay. So this matrix will belong to WBR. So this is a subspace of M and R. Okay, this is done. So that means WB is a subspace of M and R. Okay. So the D option is wrong. Okay. First, B is a orthogonal matrix. Okay. B is a orthogonal. That means B transpose into B equal to B, B transpose equal to identity matrix. Okay. This will imply that B transpose equal to B inverse. That means B is an invertible matrix. So determinant of B is not equal to 0. This will imply that rank of B is equal to n, which is equal to rank of B transpose. So in option B, if dimension of WB equal to rank of B into rank of B transpose, this will imply that dimension of WB equal to n square, which is the dimension of the vector space M and R. Okay. So if the dimension of WB equal to n square, this will imply that WB equal to M and R. Okay. That means if option B is true, this will imply that option C is also true. Okay. And option A will be wrong then. Okay. So let's verify this. Take the simplest orthogonal matrix which you know. Obviously, identity matrix is the simplest orthogonal matrix. Take B as an identity matrix. Okay, then WB will be equal to A such that A belongs to MNR. That means WB will be equal to the whole vector space MNR. Okay, so this will imply that B and C is true. Or you can show that WB equal to MNR. You can show this also. How can you show this? First, WB of R is contained in MNR. Okay, this is obvious. We need to show that MNR is contained in WB of R. Okay, so let's take a matrix A belongs to MNR. Then BAB transpose is also a matrix in MNR for some matrix B or some orthogonal matrix B. Okay, let's say BAB transpose equal to some matrix C. This will imply that BA equal to C into B, because if you multiply this equation, write multiplication by B, then this will imply that BA equal to CB, as B transpose into B is a identity matrix. Okay, so now let's multiply this equation by B transpose. We will get A equal to B transpose C into B. But this matrix B transpose CB belongs to WB. So this A belongs to the vector subspace WB. So MNR is contained in WB. Therefore, from this equation and this equation, we will have WB equal to MNR. Okay, so the option B is right and C is right. Now let's do the next problem. The next problem is, let P of x is a polynomial of degree n, be a non-constant polynomial of degree n greater than or equal to 1. Then consider the polynomial Q of x equal to integration 0 to x P of t dt, R of x equal to differentiation of P of x. Let B denote the real vector space of all polynomial in x. Then which of the following are true? The first option is Q and R are linearly independent in B. The second option is B and R are linearly dependent in B. The third option is x to the power n belongs to the linear space of Q and R. X to the power n plus 1 belongs to the linear span of Q and R. So how can we do this? Let's do it. Okay, see, the first thing is P of x is a polynomial of degree n which is greater than or equal to 1. That means P of x is a non-constant polynomial. Q of x is given as integration 0 to x P of x dx. Take a polynomial P of x as a0 plus a1x plus and so on an x to the power n Okay. For the polynomial p of x, the polynomial q of x will be equal to a naught x plus a1 x square by 2 plus and so on a n x to the power 2 and n plus 1 by n plus 1. So the degree of q of x is n plus 1, and the polynomial r of x is a differentiation of p of x. So r of x will be a1 plus 2 times a2x plus and so on n times an x to the power n minus 1. See here, the degree of the polynomial r of x is n minus 1 and the degree of the polynomial q of x is n plus 1. Now use the important result that if the set p1x, p2x, pnx, this set of a polynomial is will be a linearly independent set if the degree of all those polynomials are different. That means degree of all those p of ix is not equal to degree of some pj of x. Okay, for I not equal to j. Okay, this set will be a linearly independent set if degree of all those polynomials here are of different degree. Okay, if then this set will be a linearly independent set. So here r of x has degree n minus 1 and q of x has degree n plus 1. That means q and r are different degree polynomials. Okay, so the set q and r will be a linearly independent set. Okay, so the first option A will be correct and the second option B will be wrong. Now for the third and fourth option, you can take a counter example. See, take a polynomial p of x as 3x plus 5. Okay, here n is 1 because the degree of p of x is 1. Then q of x will be equal to integration 0 to x, this 3x plus 5 times dx. This will be equal to 3 times x square by 2 plus 5x. Okay, and r of x is equal to differentiation of p of x. That means r of x is 3. Now the third option is saying that x to the power n belongs to the linear space of q and r, and the fourth option is saying that x to the power n plus 1 belongs to the linear span of q and r. Okay, see, n is equal to 1. That means if the third option is correct, this will imply that x belongs to linear span of q and r. Okay, linear span of q and r will be equal to something a times q plus b times some r, where a and b are scalars. Okay, this will be equal to a times q of x is 3x square by 2, 3x square by 2 plus 5ax plus p times 3 times b r. Okay, so the linear span of q and r is equal to 3a by 2 x square plus 5ax plus 3b. Okay. So if x belongs to linear span of q and r, this will imply that there exists some scalar a and b such that x is equal to 3a by 2 times x square plus 5ax plus 3b. Now compare the coefficients here. We will get 3a by 2 equal to 0. This will imply that a equal to 0. Okay. And 5a will be equal to 1. This will imply that a equal to 1 by 5. But see, this is a contradiction. Here a equal to 0, equal to 5. So this is observed. Okay. So this will imply that x does not belongs to linear span of q and r. So the third option will be wrong here. Similarly, you can show that the fourth option is also wrong. Okay, this is easy. Now the next problem is saying that let A belongs to M10 of C, the vector space of 10 cross 10 matrices with entries in complex plane C. Let WA be the subspace of M10 of C spanned by the set A to the power n such that n greater than or equal to 0. Then choose the correct statements. Okay, this is easy question. Okay, one line answer. Okay, I have done similar type of problems before. Okay, so you can do these problems by yourself and you can give your answer in the comment box. Okay, so that's it for today. Thank you all.